All right, so this will be the video for limits. We are going to start out by talking about just the general limit. So the general limit is defined as the value of f of x as it approaches, as x approaches c. And so you'll take a look at roughly what the value of function is uh, as those x values get closer and closer to c. So think about if you're plugging values of the function that are either slightly less or slightly greater than c uh, into it. And then what you get out would be what approaches that limit value. Now, sometimes the limit doesn't exist for one reason or another. Some of those reasons could be that maybe the graph goes to multiple different values, one from one side or one from the other. That could cause a problem with trying to decide, well, which one would you take? And so in those cases, we say that the limit doesn't exist. There are other situations where maybe only one side of the function is actually defined, or maybe the function isn't even defined on anywhere nearby that point that we're looking at. So there are a couple of different reasons why it may not actually exist, or it may not actually have a defined value. We can look specifically at different restrictions on the limit, such as looking at it from the right side or looking at it from the left side, which basically means looking at it on the right side of the number line or left side of the number line for the number specifically that we're looking at. So right side limit has to do with x approaching c from all values greater than c. So as you're approaching your limit value, you would only be looking at the values of x which are larger than the value that we're approaching. And similarly for the left side, it means all the values of x which are less than c as it approaches c are the values that we're interested in. And then you would look at what the values are output by the function for that sequence that approaches c. So those are the left side, right side, and just the general limit kind of ideas that you guys should have. There's also a theorem that defines, or a theorem that tells you kind of whether or not the limit in general will exist. And we look at both the left side and the right side limits in order to determine that existence or non-existence. So if you have the limit from the left side equal to the limit from the right side, and it has the limit value of L, then the limit in general of the same x approaches c would be equal to L, and it would exist. And we know this the other way around as well. If the limit as x approaches c of f of x is equal to L, then we know that the limit from the left and the limit from the right must also be equal to the value of L, and they must exist as well. And so they're both ways, it's a conditional statement. So they happen at exactly the same time or anywhere on the function where one would exist, you would also have to have the other condition. And so anytime that we have the situation, like I kind of alluded to at the beginning of this, where the limit as x approaches c from the left is not equal to the limit as x approaches c from the right, then we would say that the limit of f of x, or limit as x approaches c of f of x does not exist. Okay. So there are some limit properties that we can talk about. There's the limit as x approaches c of a constant k. That case, there's no x value associated with that function. So the value of the limit would always be the value of the function itself, which would be k. In the case of a function where it's just x, the limit as x approaches c of that function would be equal to c, mainly because anywhere that you've got that function of just f of x equals x, and you're approaching the value of c, the function will output values that approach c as well. So that's the idea behind that one. With limit of x approaches c of f of x plus g of x for two arbitrary functions, then we would have limit as x approaches c of f of x plus limit of x approaches c of g of x. So you can distribute the limit across two different functions that are being added together, and the same would apply for if we were taking the difference of two functions. So if instead we had f of x minus g of x, we would have the situation where it's limit of x approaches c of f of x minus limit of x approaches c of g of x. Next, we would go to pulling out a constant from a limit. So if you had the definition or the situation where you're looking at limit of x approaches c of some constant k times a function f of x, then you would get the situation out where it could be said that k, that constant, can be multiplied by the limit of x going to c of f of x. Next, we'll have the quotients. So we can look at the quotient of f of x over g of x as we take the limit of x going to c. We can distribute the limit to both the numerator and the denominator of this quotient to get limit as x approaches c of f of x over the limit as x approaches c of g of x. Next, we can look at the limit as x approaches c of the nth root of f of x, and that'll be equal to the nth root of the limit of x going to c of f of x. And then also we can say that if f is a polynomial, then the limit as x approaches c of f of x equals f of c. So basically, anytime you have a polynomial, you're able to take the value of c and plug it into the actual function to get out the limit value of what it should be. Next, we'll talk a little bit about the indefinite form. So the indefinite form is when you would have 0 over 0 if you tried to take the limit. So if your numerator ends up having the limit of 0 and your denominator ends up having the limit of 0, you'll get this indeterminate form. And there are a couple of cases as to what could cause this. One of them could be a removable discontinuity. The other one is non-removable discontinuity. And we can take a look at a couple of the examples that we have here. So example 1 gives us an example where the issue for our indeterminate form could be removed. So we'll look at x squared minus 4 over x minus 2 over on the right side here. And this can be, numerator can be factored into x minus 2 times x plus 2. After factoring, we'll end up with this limit that's right here. And you'll notice that on the next line, I've rearranged a couple of the terms and crossed out the cancellation with the numerator and the denominator for that x minus 2 term. And that leaves us with just x plus 2 as the value of the function that we're going to be taking the limit of. And if you plug in or use the property that we just talked about, that polynomials can have the value plugged into the function to find the limit of them, then we can see that the x going to 2 could be 2 for that x, which would make it 2 plus 2, which equals 4. And so the limit in this case, where it would be a 0 over 0, if we just took the limit of the top, that indeterminate form can be turned into an actual evaluatable limit if we remove the issue that was causing the 0/0 situation. In another case, it may not be possible to remove that. So we can look at the example for number 2 over here on the left side, and we can see that we are not able to remove this particular issue, which causes the indeterminate form. Part of that is because we're getting different values from the left side limit and the right side limit. So if we look at values of x which are slightly less than -1, we'll get values that come out of this function which are going to be equal to 1. That is because x are all right. So I'm going to be switch these around really quickly. So this one's going to be 1, and this one's going to be -1. And I tried to change up the example that was in the book, and I just forgot to change the sign on that because in the one in the book, they have an X in the front, which changes the sign value on it. For these particular ones, the way that I have it written, the X being slightly less than -1 will cause both the numerator and the denominator to be negative values, but the numerator has an absolute value on it, causing it to be a positive for that whole term in the numerator. That means that the numerator is positive while the denominator is negative, causing x values which are slightly less than -1 to create the function or to give the function a negative sign value overall. In the cases where we're looking at the right side limit, where x is slightly greater than -1, we're going to have the numerator being a positive value. Absolute value of a positive value is positive. And then the denominator will also be positive, which will mean that we have a positive value over a positive value, which when evaluated would be positive. So we would get the value of 1 for this case. And so that's where you would come up with limits from the left and limits from the right, which are not equal to each other. And that means that the limit in general does not exist for this particular point. Even though if we were going to look at what it would be if we plug them in and we would get 0/0, the situation in this case does not evaluate to any particular limit. It's an indeterminate form with discontinuity that's not removable. And we'll talk more about discontinuity later, but just so you know, that's what the situation would be for this particular form. All right. So let's talk a little bit about the limit of a quotient. If we're going to do the limit of f of x over the limit of g of x, then we can take a look at whether or not the limit of f of x is going to be 0. And if it's not, then we need to check and see if the limit of g of x is going to 0. Because if the limit of g of x does go to 0, that means that we would have some value of the function in the numerator over some 0. And in all of those cases where you have some value which is non-zero in the numerator over a 0 in the denominator, that value of the function will not exist, or that limit will not exist. And so that's an interesting property of the limit of quotient. And I think that just about wraps it up. So that's the end of this video for limits. And I'll see you next time.